So in this video, we're going to continue to talk about how to implement a stack based on the linked list idea. So to pick up where we left off in the previous video, we are going to write the string method. Now, a useful string method should show us everything that is in the stack, starting from the top, right? So now that basically involving that we have to walk down this linked list and visit every single one of the nodes and to kind of put their information in one string. So how do we accomplish that? Here is the code, and I'm going to kind of step through it one line at a time. So one of the most important thing to recognize, and I mentioned this earlier, and is that given just the pointer, the top pointer to the first node in the linked list, we should be able to visit all of them, all the rest of the nodes, and we should know when to stop, right? So so we're going to start at the top. So I'm going to make a temporary node that points to the top, and then I'm going to initialize the string that I'm going to return from the string to an empty string, and then I am going to loop through them, and I'm going to keep looping and move the node one node at a time until we reach the very last node that when node is actually pointing to none. And that's why the condition for the loop is while the node is not none, and we'll keep looping this. And so let's step through this. What happens is, so while no is not none, obviously no is pointing to the top. It's not none yet. So the condition is true. We kind of get into a return string. I'm going to concatenate whatever the string representation for the current node is, and in the return string. So what a string return string should have, it should contain the information about node 1, right? And then I advance the node to point to the next pointer of the node itself, which means I'm going to move node to here, right? And then I'm going to repeat this. It's in a while loop, right? So I'm going to check the condition again and say, hey, is it none? Well, it's not none. So I'm going to repeat what's inside here. I'm going to concatenate the string representation of the next node, node 2, into the return string. And then I'm going to advance again the node to node.next. So now the third node, same thing. And the interesting part here is when I do node equal to node.next, well, node.next is pointing to none. So I know then is, after I execute this line the third time, it's going to point to none. And when it goes back to the beginning of the while loop and check the condition, now node is none. Then this time it's not true, it's false. And so it will exit the loop and it will return the string that has all the information of all the nodes concatenated together. So now that we have a basic implementation of the string, one of the questions we ought to ask ourselves is, does it work in the corner case of an empty stack? So does it work? Well, the answer is kind of depends. So if the stack is empty, it's not going to execute this loop at all. So in that case, we'll just return an empty string. So, and if an empty string for an empty stack is okay, then this works. Okay, so next two question is, then we kind of already mentioned, how do we see if a stack is empty, and then how do we see if the stack is full? All right, so pause the video and think about these. Okay, so here are the answers. So for the empty, it should be very straightforward that if the top is none, then it's empty. Otherwise, it's pointing to at least one node. Now, is full is, you can call it a trick question. So it really doesn't make sense to implement is full, right? So one of the reasons that we went with a linked list-based stack is that we can just keep growing it to store more and more data. Um, and that's a huge advantage compared to the array-based stack, which we have to allocate all the capacity at upfront, and if we reach the full capacity, then we cannot really add more room to store more data. Now, of course, nothing can grow kind of forever, and so in case of linked list based stack, I mean, we could grow so large that we actually run out of memory in our computer. But how to handle out of memory situation, that is a very different problem. So we are not going to be concerned with that. So at this point, we are pretty much done talking about most of the code in pictures in the linked list space stack. So I'm going to show the code now, and well, actually run it. Uh, every most things here are basically what we just discussed. So for the test code, I allocate a stack, and I'm going to print out right away to see if it's empty. It should be, right? And then I'm going to just push 2 new nodes to it, and I'm going to print the stack. After pushing 2 nodes in, I'm going to pop one of them, and then I'm going to print the stack again after the pop, and then check if it's empty. So it kind of exercises most of the code path that that was implemented in the stack. So there it is. So when we first started, yeah, the stack is empty, and we push 2 nodes. So and now, so we pop one of them. We would expect this to be popped. So, and that is indeed the ID of the node that is popped off the stack. And after that one pop, we have one node that is left on the stack, and the ID of that node should match the second node on the stack, and that is this one. Yes, that's exactly what it is. And we check if it's empty. It's not quite empty because it still has one node on the stack.